Okay, let us start with the next lecture, which will be about the cryptocurrency of Zcash, and which would Zcash is based on the technique of zk-SNARKs. So we'll also talk about zero-knowledge snarks, and we'll also talk about POW, which is different than the classical crypto puzzles of Bitcoin. So the use of zero knowledge in blockchain is typically based on non-interactive zero knowledge. So the examples in the tutorial and the lecture on zero knowledge, we mostly looked at the interactive zero knowledge, where there were several rounds of interaction between the prover and the verifier. However, it doesn't have to be. There are also flavors of zero knowledge without interaction. Such flavors of zero knowledge is called one-shot ZKP. So what is one-shot ZKP? It means that the prover stores something, for example, on blockchain, and the verifier can verify it without any interaction with the prover, just based on the proof stored on blockchain. And indeed, it's particularly suitable for blockchains where transactions are verified by individual nodes and there is no central authority to oversee the verification process. And usually there is no channel between whoever put the information on the ledger and whoever verifies the ledger. There's no communication channel. So the idea of non-interactive ZKPs comes from the seminal result of 1988, that actually a common string shared between the prover and the verifier is sufficient to achieve computational zero knowledge without requiring interaction. So there must be some shared string. Okay, so how do you sort of sneak this shared string in? Can you just store it on blockchain? Do we need some other ways to do it? And this question gives rise to actually to different techniques to provide non-interactive zero knowledge. So impossibility results, so for example, impossibility result that without such a string it's impossible to achieve such a zero knowledge. So such impossibility results have eventually led to multiple solutions with different trade-offs. And as of today, there are three most popular proof systems for non-interactive zero knowledge which are used in the context of blockchain. They are called zk-SNARKs, zk-STARKs, and bullet proofs. How do we compare between the three? So what do we want? We want the sort of the computation for the prover, the production of the zero knowledge to be fast. We want the verification to be fast, and we want the size of the proof to be small because it needs to be stored on blockchain. So those are the three desirable properties for non-interactive zero knowledge proofs: the speed of producing the proof, the size of the proof, and the speed of the verification. And herein lies the trade-off. You can see that bullet proofs, they're probably the worst of the bunch. They have the slowest proof production speed in the order of 30 seconds. They have the slowest verification speed in the order of 1,100 milliseconds. And the size of the proof is in the order of small number of kilobytes. So it's medium. Then we have zk-SNARKs, which are very fast to produce proofs, the fastest to verify, and the smallest in terms of size. And in zk-SNARKs, the production of the proof is even faster, but the difference is not big. The verification is also very fast, just a bit slower. However, the size of the proof is quite big, maybe prohibitively big for it to use in blockchain. Because of this, zk-SNARKs is the most common technique to use in blockchain. What's the catch? The catch is that it requires more setup than the other techniques. So more configuration. So that's basically the idea of zero-knowledge proofs, the implementation of zero-knowledge proofs in the context of blockchain. Okay, so that's like a background behind Zcash. Now let's move to discussing Zcash. What's the motivation? What was the criticism? Why did the authors of Zcash thought it would be a good idea to come out with Zcash? What was their criticism of Bitcoin? Well, they said that anonymization in Bitcoin was not enough. Bitcoin can be, there are several reasons why, or there are several things which can help the attacker trace transactions. First, there is the graph of transaction, so the same criticism as in Monero, but it goes further. They also say the transfer values are in plain text. So if we see, for example, that there is some very weird amount of like 239, for example, Bitcoins is transferred in one transaction, and then even if we hide the trace, we see another transaction which uses 239 Bitcoins. Well, that's an unusual value. And if it's used in both transactions, there's high suspicion that both transactions are connected. And there is a third element which helps the attacker, and that's transaction dates. So transactions in Bitcoin, a significant amount of Bitcoins are spent very fast after they're being transferred, right? So we can correlate transactions also based on the timing. So those are the three factors that sort of motivated them to think about Zcash. Okay, so they had an inspiration. They were looking at cryptocurrency exchanges. You know that, so what cryptocurrency exchanges do? They have high volume of transactions, so they take, like they store wallets for many customers, and then they facilitate operation using nice graphical interface and other facilities. And like the idea of crypto exchange, if it's a big crypto exchange, that maybe some trade can be done internally without even going to Bitcoin, right, between two users of the same crypto exchange. So, so those crypto exchanges usually do bulk operations. So because they do bulk operations, it helps obfuscate the history. Right, because imagine that you take like 5 different transactions and you batch them together in a single transaction. So now instead of like you had one transaction, so Alice was transferring to Bob, Carol was transferring to Derek, and Eve was transferring to Oscar. Okay, 3 transactions, but could be many such transactions. Now, instead of 3 transactions, we have a single transaction. So what crypto exchange does, it batches the transaction, instead produce single transaction. which takes inputs from Alice, Carol, and Eve, and transfer funds to say to three others. By this, so this batching helps with obfuscation, right? Because now it's more difficult to understand who transferred to whom. Now we have three inputs, three outputs. How do they correlate with each other? That helps obfuscation. So that was their idea. It also, another reason why cryptocurrency exchanges help is that it introduces delays. So like one of the reasons for traceability is transaction times. But what crypto exchange can do, so it's batching. It means that like the crypto exchange would get the first transaction from Alice to Bob. It would not immediately put it in Bitcoin. Instead, it would wait for further transactions. So it would wait until it received another transaction, for example, from Carol to Derek, and from Eve to Oscar. And only after this delay, it would produce a batch, a single transaction, which is a batch of individual transactions. And this mode of operation introduces the delay. And this delay also helps with the obfuscation. What's the problem? So does it mean that crypto exchanges solve the problem? No, well, the problem is that security and privacy. Crypto exchanges are typically centralized and run by an operator, and that operator has access to all your data, right? So that part is not good in centralized crypto exchanges. Therefore, their idea was to come up with a decentralized crypto exchange, a decentralized mix, something similar to crypto exchanges, but without any centralized actor responsible for those operations. So how does it work? It employs one-shot zero-knowledge proofs to prevent transaction graphs analysis. So the proof is to show that the particular coin is valid. You do not reveal the source. You do not reveal the output, which is used as the input. You do not reveal it. But you prove that there is a correct output. However, zero coin doesn't hide the amount. And zero coin had a few additional problems. First of all, every token in zero coin has the same value, so you cannot transfer, like in Bitcoin, a single token may be many Bitcoins. In zero coin, a single token is always one unit of currency. So if we want to transfer a lot of currency, we need to have a lot of inputs, a lot of outputs, doesn't scale. And another problem with the zero coin was poor performance. So one proof was occupying order of 45 kilobytes of storage and was taking 1 second to verify. So not very fast. So then, pretty much the same authors came up with the idea of zero cash. Zero cash was like an evolution of zero coin. Zero cash hides denominations as well. So it not only mixes transactions, not only uses zero knowledge proofs, but it also hides how much. And it allows for anonymous transactions of variable amounts, right? So not just one unit of currency, arbitrary amount. And the proofs are taking only 1 kilobyte of storage instead of 45 kilobytes. And we're taking 5 milliseconds to verify. So the performance was also much better. So this is what zero cash provides. But how does it work? Here's the basic idea of zero cash. So first of all, user needs to make a proof of funds. Zero cash also allows for interoperability, so it could be a certificate of deposit which allows a user to convert a specified number, for example, of bitcoins into the same number of zero coins. That would be a proof of funds. Okay, but now the real idea starts. In order to make a transfer, a user of zero coin creates a unique coin ID called serial number, SN. Next, the user creates a random secret, and then it creates what's called a coin commitment. Coin commitment is a one-way computation, which takes into account the random secret and the serial number of the coin, which again is supposed to be unique. And then the commitment is like a tuple, which consists of three elements. The commitment, the commitment is just a computation. Then the user creates a tuple, which consists of three elements: the commitment, the serial number, and the secret. And then the user would commit a transaction containing the commitment, but not the serial number or the secret, to the ledger. So the commitment is visible for all to see, but not the secret. And then how can another node spend that coin? It is spent by posting a transaction which would contain the serial number and the zk-SNARK proof of I know R, such that the commitment appears on the list of coin commitments. The list of coin commitments meaning in the ledger. So again, the sender, in order to spend the coin, the sender needs to post a transaction which would disclose. So previously there was just a commitment on the ledger. But in order to spend the coin, the sender needs also to disclose the serial number, but not the secret. The serial number and the proof, the zero knowledge proof of the fact that I, the sender, know the secret, such that the commitment appears on the ledger. So the list of, that's the basic idea. This is how you implement zero cash, and this is how the system works. Of course, on top of that basic ideas, they have many extensions and optimizations. For example, in the basic version, you store the commitment just on the ledger, in a list of commitments. And the commitments can be manifold, and the list may grow very fast. So it's not very scalable with respect to storage of commitments. So the extensions of the basic idea, the first extension is more efficient verification of commitment inclusion in the list of coin commitments. So now you don't need to sequentially scan all commitments on the ledger in order to verify if a given commitment is there. Instead, they use Merkle tree to organize all commitments, and then they could search for the following: I, the sender, know the secret such that commitment is a leaf in a Merkle tree with the given root. And that operation is much faster than sequentially going over the list of all commitments. also, in the basic idea, I was only talking about coin ID, about coins, right? And the coin in the basic idea just have the same amount, 1 unit of cryptocurrency. So another extension is support for arbitrary denominations while obfuscating the amount. And yet another idea is the ability to convert minted coins back to Bitcoin. The system is very cryptographically involved, so the proofs of verification take many pages, so it would be difficult for me even to explain the intuition behind all the steps. I'm just giving you the overview. So that's what I wanted to say. I mean, this is just a brief overview of zero cash. Now, additionally, I would, so now I'm switching away from zero cash and I'm talking about alternative mining. So let's take a look at a brief history of mining trends. Between 2009, when Bitcoin came out, and 2012, all mining was done on CPUs, essentially. Because Bitcoin was not so popular at the time, and the basic idea was to use CPUs in the beginning. And since there was not sufficient interest, people were not coming with the ideas how to do it more efficiently. However, in 2013, it was shown that application-specific integrated circuits, chips, called ASICs, can be much faster than CPUs and GPUs. So the mining based on them in Bitcoin, they would solve crypto puzzles much faster. And by that time, Bitcoin became popular, and there were many miners. There were also many rich miners who could afford to buy ASICs. Of course, ASICs are more expensive than CPUs and GPUs. So what happened is the following trend. Because of the price tag, the Bitcoin network was gradually taken over by wealthier individuals and players and enterprise-level mining farms. So you would have those huge mining farms, say in China, in Canada, certain provinces where the electricity is cheap. And all that results in a centralization of Bitcoin. So we previously discussed that fairness is a very important element and very desirable property of cryptocurrency. Well, this trend, due to use of ASICs, Bitcoin was losing some of decentralization and some of fairness. Okay, so what would be the solution? In 2016, the idea of Equihash was proposed in an academic paper. In all fairness, they were not the first to consider such ideas, but they were the first to make it practical. So what was the idea? In crypto puzzles, you just need CPU, or you just need a computational unit. You can do computation on CPU, GPU, on ASICs, but you only need computational unit. What you need is to compute hashes, and fast. Hashes themselves do not take a lot of space. Even the inputs to hashes, in principle, they could be of arbitrary length, but in Bitcoin, they do not take a lot of space. Therefore, computing one hash is very fast, and computing many hashes just requires doesn't require a lot of resources apart from computation. what was changed in Equihash and other mining algorithms is to consider a problem where you would need not only computational units, but other resources as well. Okay, what other resources? A lot of memory and memory bandwidth, fast access to memory. And those are much more difficult to scale compared to computation. Because you cannot easily put many terabytes of memory in a single computer. So how did they do it? In Equihash was based like a practical memory-bound algorithm based on the generalized birthday problem. I'm not going to present the generalized birthday problem, in detail. But the idea is that you have like two matrices or two long vectors, and you need to find a pair of vectors whose multiplication would result, scalar multiplication would result in 0, for example. And you need to find all such different pairs. So it turns out that in order to do that, you need a sufficient amount of memory. And this is why, for example, the algorithm in Ethereum is different from crypto puzzles in Bitcoin. Again, with the same purpose of preventing decentralization. Or prevented centralization, sorry. Was it the end of the story? Does it mean that centralization didn't happen for Ethereum and for the others? Well, in around 2018, there came ASICs for Equihash. So they were doing much better than common purpose. But still, their improvement compared to normal computers was not nearly as large as the improvement of ASICs compared to CPUs. And therefore, they exist, they are used, they are not as effective as ASICs in Bitcoin. And for this reason, the centralization in Ethereum is not considered as much of a problem as centralization in Bitcoin. And as a matter of fact, most of the mining in Ethereum today is done by GPUs. Not by CPUs, not by ASICs, but by GPUs. Okay, this is the end of this lecture. Again, it's just an overview of mining trends. Just to study the problem of Equihash would require at least one additional hour. So we decided against including the details in the course. But the paper is quite nicely written, and I recommend it to everyone. What is the view of the miner in a particular blockchain, sir?
What that block? What kind of function
block is a batching transactions, right? Right. So again, in the lecture on Bitcoin, we talked about scalability of consensus and how much of a problem it is. So, and all different techniques that are used to improve the scalability. So one of the techniques is essentially, so imagine we have 100 transactions, right? So we can run a separate consensus on each transaction, or we can put them together in a single block and run consensus just once for the entire block. It turns out that running consensus one time is much cheaper than 100 times.